Welcome students. Now we'll see little bit more about uncertainty principle. Okay, in the last video on uncertainty principle, we have seen that according to the uncertainty principle, it is impossible to find the position and momentum of a particle simultaneously accurately. Okay, we have listed out some canonically conjugate pairs. What are those canonically conjugate pairs, right? X comma px. Uncertainty principle is applicable for this pair only, or y comma py, okay, or z comma pz, or energy comma time, or angle comma angular momentum. These are called canonically conjugate pairs. Uncertainty principle is applicable only for the variables inside this pairs. You cannot interchange the variables from different pairs. Okay, that is right. The uncertainty in the variables of canonically conjugate pairs means here x and px are there. What is uncertainty in x? Delta x means the uncertainty in the position of a particle if it is delta x, and uncertainty in estimating its momentum is delta px. Uncertainty principle says it is greater than, it cannot be less than h bar by 2, means it can be greater than or equal to h bar by 2. So what is the minimum value of that uncertainty? Minimum value of that uncertainty is h bar by 2. It can have any value greater than h bar by 2. So most of the times in solving problems, as we are only interested in the order, okay, we'll take it as h bar. Okay, in most of the problems we'll take it as h bar. If he specifically asks about minimum uncertainty, then we have to use h bar by 2 only. Okay, now what is this uncertainty, right? Why I cannot find the position and moment of a particle, right? In our everyday life, we don't see any difference. See, when a car is moving, right, I can know its position accurately. I can find out its momentum, because if I know the mass of the car, okay, from the manufacturer, if I ask, he will tell me. Okay, if I ask its driver what velocity he is going, he will tell so and so velocity. I can estimate its momentum and I can see its position with my eyes clearly. Means I can find out position and momentum simultaneously. Okay. Then why this uncertainty principle is saying that you cannot find the position and moment of particles simultaneously accurately means, right? Go at microscopic level. When we go to microscopic level, the situation will be different from what we see in our everyday life. Okay, right? Now, de Broglie said that every material particle has some matter wave associated with it. Okay, what is a wave actually? Wave is something like this. Okay, a pure sine wave or cosine wave, whatever, depends on the origin you choose. Okay, right? It extends from minus infinity to plus infinity. Minus infinity to plus infinity. Okay, this is a pure sine wave. If I say that a particle is equivalent to a wave, okay, wave is an extended phenomena which can go from minus infinity to plus infinity. When the situation is like this, where is the particle? Okay, where is the particle means it can be present anywhere from between these limits of minus infinity, entire domain from minus infinity to plus infinity, particle can be present anywhere. Okay, what's the advantage here? I can find out its momentum very accurately, because momentum P equal to h by lambda. Once I know the wavelength as accurately as possible, right, I can estimate its momentum also. If somebody gives me such a pure sine wave like this, right, I can make 101 measurements on lambda. I can measure the wavelength from here to here, or from here to here, or from here to here, or from here to here, like this. I can make 1000 measurements on lambda. Okay, the best possible values or the most appropriate value I'll take. I can calculate the momentum perfectly. But what about its position? Okay, position I cannot specify. Particle can be present anywhere. Okay, from minus infinity to plus infinity, always. It has equal probability to be found anywhere in that region. Means it's not square integrable, if you say. Okay, once I go into quantum mechanics, we use the word called the wave function should be square integrable. Okay, integral minus infinity to plus infinity mod psi square dx should be less than infinity, we say. Here we get that probability of finding the particle as infinity. Okay, infinite particle means what? Particle is present everywhere in the universe always, which is meaningless. Okay, who can be present anywhere in the universe always, omnipotent and omnipresent? Okay, only God. Okay, right, means that every particle becomes a God. Okay, which is not acceptable in physics. Okay, means particle is a localized quantity. If I have particle like this particle has a finite extent in space. It is like this. Okay, it is starting from here and ending here. What is the probability of a particle? Probability of finding the particle lies only between these regions. What is the probability particle is not present here, particle is not present here. But what about this de Broglie wave? De Broglie wave is present everywhere. Where do I cut the wave? Okay, because de Broglie said that it is equivalent to a wave. Wave can be anywhere from anywhere. Okay, means I have to bring down this extended phenomenon called wave to a localized phenomenon called particle, because particles are localized. Okay, this particle is there. What is the particle? Extending from this point to this point only. There is no particle here. There is no particle here. Okay, but its wave, matter wave, should have existence everywhere. That is wave property. Okay, this is a particle. Two entirely different quantities should be correlated here. Okay. Right, when he said that particles behave like waves, that earlier that problem was not there. Why? Particles are different, waves are different. People thought that wave phenomenon is a totally different phenomenon. Waves are totally different phenomenon. Particle mechanics is totally different. That's why in your BSc first year, people separate mechanics and oscillations and waves. Okay, right, here we deal with amplitudes, frequencies, intensities, etc., etc. Energy only. Here we talk about momentum, mass, conservation of linear momentum, conservation of angular momentum, like this. We don't take conservation of linear momentum into wave phenomenon. We don't talk about intensities, frequencies of particles, etc. But after this de Broglie's concept, people have to relate between particle and wave. But what is the problem? Wave is an extended phenomenon. Wave goes from minus infinity to plus infinity, whereas particle is a localized phenomenon. Now we have to correlate these two things. I have to correlate these two things. Okay, if the wave, if I take like this, I can find out its momentum very accurately, because I can estimate its lambda. I can make 1000 measurements. Okay, because wave is giving me that provision. Okay, I can estimate its momentum, but what about its position? I cannot specify where the particle is from here to here. Here to here means what? Not on the board. From minus infinity to plus infinity. Okay, so what do? I have to, compress this wave. I have to compress this wave. I have to localize the wave. Okay, how to localize this wave means we have studied in simple harmonic motion. Okay, people study what is known as a phenomenon of beats. Okay, when two waves of slightly different frequencies, right, with suitable phases superimpose each other, the amplitude of the wave becomes alternately maximum and minimum. This everybody must have studied in your +2 level. Okay, right, when two waves of slightly different frequencies, okay, one wave like this, another wave like this. Okay, if these two waves superimpose each other, okay, the resultant amplitude will be, right, maximum, minimum, like this. That's called one maximum and one minimum is known as one beat. Number of beats per second is known as beat frequency, etc., etc. Means the situation will be like this. Okay, when two waves of slightly different frequencies superimpose each other, amplitude of the resultant wave will become maximum and minimum like this. Maximum and minimum like this. Okay, at some points it becomes maximum, at some point it becomes minimum. Okay, now if I represent this, if I consider only the amplitudes, amplitude is becoming maximum and minimum. Maximum and minimum like this. One maximum and one minimum is known as one beat. Number of beats per second is beat frequency. Okay, but here also amplitude is maximum throughout the case. Okay, if I add 3 more waves, 4 more waves, I keep on adding, right, more and more waves of slightly different frequencies with correctly chosen amplitudes and phases, the situation is that mathematics says that the possibility of localizing the wave is possible like this. Okay, right, means now the wave has no amplitude from this point. It has no amplitude from this point onwards. Wave has having some measurable amplitude only between these two regions. Means ultimately I could compress the wave to some region. I could localize the wave to some region. Okay, right, but still the particle can be present anywhere from here to here. Earlier it is much better than the earlier situation. Why? Here particle can be present anywhere from minus infinity to plus infinity. Now I'll say wherever this region of maximum amplitude is there only the particle will be found. Means this becomes my delta x. Okay, uncertainty in finding the position of the particle. Okay, I can say there is no particle beyond this region. I can say there is no particle beyond this region, but where exactly the particle is between these two limits, that I don't know. So uncertainty in my measurement of position of the electron is confined between these 2 points. Okay, this I'll call it as delta x. But What about delta P? Okay, how did I get this wave phenomenon? Okay, by combining, not here, if I combine two waves, the situation is like this. I'm combining some 10, 15, 100 waves, okay, of slightly different wavelengths. Slightly different wavelengths means k equal to 2 pi by lambda, the propagation constant, okay, different k values. Okay, which k value I should consider for this? I'll call this as a wave group or a wave packet. This wave packet is a resultant of so many superposition of so many waves. Okay, which k value, which lambda value I should consider? Okay, my the lambda values which I should consider will be increasing here. 100 or 200 lambda values when I superimpose, I'll be getting such a wave packet. Okay, means my k value, spread of k values is increasing because there are so many k values to be chosen. Which k value I should choose? Okay, which k value means again, right, into 2 pi by 2 pi, linear momentum P equal to h bar k according to de Broglie relation, right? 100 k values means 100 different p values. Okay, when I am compressing the this wave phenomenon, I'm localizing the wave phenomenon. What is happening? In order to localize, I have to consider more and more waves of slightly different frequencies. Means the k values I should consider, it keeps on increasing. Momentum values I should consider will keep on increasing. That is, the spread in the k value, delta k, keeps on increasing. But what is happening to spread in the position of the particle? Delta x is decreasing. Okay, so I'm not doing an experiment. Okay, before doing the experiment only, whether I can find the position and momentum accurately or not, simultaneously, leave that case. Okay, let us see the situation. First of all, particle is like this. Okay, if I don't put any restriction, or if I consider a single wave, the situation becomes meaningless. Okay, particle can be found anywhere. So in order to localize the particle, I know that this pen is confined only between these two ends, that's all. Okay, its wave will be from minus infinity to plus infinity. I should transform that wave phenomenon into this confined entity or localization. Okay, how can I do that? By adding 101 waves. Okay, 101 waves of slightly different frequencies means my k values will be different. I have to consider which k value I should consider. There are too many k values to be considered. That is, as delta x is decreasing, delta k is increasing. Okay, I can further add some more wavelengths. Still confine the the position of the particle like this. If I add 1000 more, okay, slightly different wavelengths, the wave packet will become like this. Now the probability of finding the particle, right, is the region in which the particle can be found is extremely small. Okay, delta x is small. Okay, but what is happening to k values? How many wavelengths I am considering? I have to consider some thousands of wavelengths. Okay, because this type of representation phenomenon is possible with thousands of wavelengths only. That is, my delta k value keeps on increasing. When delta x value, right, is decreasing, delta k value is increasing. That is, right, delta k is found inversely proportional to, they are in this inverse relationship. Okay, right, when you keep on decreasing the delta x, answer, you want the particle to localize more and more, you want to find the position of the particle precisely, you are decreasing delta x value. In order to decrease the delta x value, you have to consider more and more slightly different wavelengths. Okay, that is, momentum spread is increasing. Okay, or delta k spread is increasing. So we can say that common sense says what? Delta k and delta x are having inverse relationship. Okay, that is, delta k into delta x is of the order of 1 approximately. Okay, delta k into delta x is approximately equal to 1. Now I'll multiply with delta k, p equal to h bar k. Okay, right, so delta p equal to h bar into delta k. All right, okay, so delta k equal to, right, p by delta p by h bar, delta k delta p by h bar, that h bar goes off, delta p into delta x is approximately is of the order of h bar. Uncertainty principle, right? Heisenberg has proved that the minimum value of that uncertainty is RMS values of the product of the uncertainties. Okay, if you take the accurate values, RMS values, it cannot be less than h bar by 2. Okay, so I can write here delta px into delta x is of the order of h bar from this expression. is of the order of h bar from this expression. Okay, so it will become clear that when you have to treat the particle as a wave, okay, automatically by nature when you are trying to localize the particle, right, means are decreasing the uncertainty in its position, right, what will happen to the spread in the wavelength, the spread in the momentum will keep on increasing. If you want to have the momentum to be found accurately, you want to reduce the spread in momentum, means you will not consider hundreds of wavelengths, you will consider very few number of wavelengths. What is happening to the position uncertainty? The spread of the wave packet is increasing. So this I'll call it as a groove, or I'll call it as a wave packet. Okay, so according to quantum mechanics, the particle, right, is not a single wave as de Broglie has postulated, but of course de Broglie concept got modified by quantum mechanics like this. Okay, it said it is not possible, right? It is nothing but a combination of large number of waves. You call it as infinite number of waves of slightly different frequencies with slightly different amplitudes and chosen phases, we call. Okay, such that the particle can be localized. Now suppose a particle is moving with a velocity v. I say that this wave packet is moving with that velocity. The velocity with which this wave packet moves is called group velocity. The velocity with which the associated particle moving is known as particle velocity. Okay, it is like one coin having head and tail. Okay, I just toss the coin like this. If you are looking only at the head, you say that head is going up and coming down. Okay, the classical physics says particle is going up and coming down, whereas quantum physics says he'll be looking at the tail. Okay, he says tail is going up and coming down, but that head and tail are nothing but two faces of the same entity called coin. Okay, one person is looking at from particle point of view, other person is seeing from the wave point of view, or he says wave packet is going up, coming down. Whatever it is, coin is only one, isn't it? Let you call it as a particle or a wave. The velocity with which that particle going up and coming down must be same as the velocity with which wave packet is going up and down, because head and tail, they cannot be separated, isn't it? When head is going up, tail is also going up in the coin. Okay, both are nothing but two different versions of the same entity. Okay, so we should prove that the particle velocity is equal to group velocity. Okay, that can be shown now very easily. Okay, but uncertainty principle, right, it is inherent in nature. Okay, right, there is nothing like here, there is no question of the accuracy with which you can find out its position, the accuracy with which you find its momentum. However accurate its experimental setup is, inherently nature is like that. Okay, particles are represented by wave packets. That wave packet will have finite spread. Okay, right, now how is that wave packet arranging? By considering infinite number of waves of different wavelengths, means infinite number of momenta, right? The more you increase the number of waves, okay, the better will be the position. Okay, right, you are not accurate about the position, means if you consider the spread of the wave packet by decreasing the wavelengths, your uncertainty in wavelengths may decrease, but uncertainty in the position will keep on increasing. So there is no question of whether I will be able to find it with my most accurate, however accurate our experimental technique is. Okay, however good our experimental technique is, inherently nature has this uncertainty. Means what does it mean? The particle can never escape its wave nature. Particle can never escape its wave nature. Particle has inherent wave nature in it. That is, I can say that entire matter is in a state of condensed vibration. Okay, the matter itself is in a state of condensed vibration. What we seeing as a particle is not a particle, but a state of condensed vibration inside it. Okay, right, means the particle cannot leave its wave nature and go forward. It's like a dog running. Okay, when dog is running, tail also should go along with the dog only. Tail cannot leave the dog and go forward. Okay, right, means the head of the dog, the tail of the dog should be together when they are running. Okay, right, they are not inseparable. Okay, classical physics looks at the head of the dog, quantum mechanics looks at the tail, not tail of the dog. Quantum mechanics takes the whole thing. Okay, right, only thing is this and this cannot be separated. Particle and wave natures cannot be separated. Okay, they are inherently at the same place, one and together always. Okay, whether you look at that wave nature prominently or whether you look at that particle nature prominently depends on our problem. At macroscopic level, this wave nature becomes insignificant, right? Particle aspect will be dominating. At microscopic level, when you are going into subatomic world, okay, when you are talking about electrons, protons, neutrons, etc., right? It is that wave nature becomes more prominent. Okay, particle aspect will be going into background. Means at macroscopic level, it is delta P, right? Which is very what you call this momentum aspect or particle aspect will be dominating, right? Wave aspect will recede into background. Okay, at microscopic level, it is that wave aspect which comes into dominance. Okay, particle aspect will be receding into the background. Okay, right now. So inherently, uncertainty principle says what? Inherently, right, the nature has this uncertainty. It is nothing to do with our ability to measure. Okay, however capable you are in making measurements, that that uncertainty between the position and momentum will always exist. So delta x is inversely proportional to delta k, we say. Okay, right, or delta x into delta k is of the order of h, is the order of 1. If I multiply with h bar, delta p into delta x will be of the order of will be order of h bar. Okay, so uncertainty principle is the most fundamental principle. Okay, now the velocity with which, in classical point of view, the velocity with which the particle is moving is known as particle velocity. From quantum mechanics point of view, the velocity with which this wave packet moving is called group velocity. In general, right, what is velocity in general for a wave? Right, wave velocity v equal to c equal to nu lambda. Okay, v equal to nu lambda, so nu into lambda, multiply and divide with 2 pi. Okay, that is 2 pi nu into lambda by 2 pi. Okay, 2 pi is, nu is nothing but angular frequency omega. 2 pi by lambda is k equal to 2 pi by lambda is called wave constant or propagation constant. Okay, so it is lambda by 2 pi will be 1 by k. So in general, wave or phase velocity, right, in general for any wave is omega divided by k. Okay, when you divide angular frequency with k, or when you multiply frequency with wavelength, you will get the wavelength of the velocity of that wave. Whereas its group velocity is written like this. You have to, in order to get the group velocity, you have to differentiate omega with respect to k. That is, right, when wave or phase velocity of a wave, the velocity with which its instantaneous phase keeps on changing, right, is omega by k, right? Its group velocity, right, when so many waves superimpose each other and forms a group, the velocity with which that wave group or packet moves is obtained by differentiating omega with respect to k, or d omega by dk, right? Okay, now we are talking about what you call the particle aspect of nature, particle aspect of wave and wave aspect of particle. Light behaving like a particle, quantum theory. According to quantum theory, energy of each light packet is equal to h nu equal to h bar omega. Okay, this is waves behaving like particles, that is Max Planck's quantum theory. Exactly opposite one is de Broglie's concept, that's particles behave like waves. Okay, that concept is P equal to h by lambda. Okay, that is nothing but h bar into k into 2 pi by 2 pi. If I do, I'll write it as h bar k. So what is, right, E equal to omega equal to, right, E by h bar. So what is the group velocity, right, Vg equal to that packet of light, right, d by dk of omega. Omega equal to E by h bar. H bar is a constant, 1 by h bar into de by dk, I'll write. 1 by h bar into d by dk. Now P equal to h by lambda equal to h bar k. If I differentiate this, dp equal to h bar is a constant, dp equal to h bar into dk. So here in the denominator we have h bar into dk. So Vg is equal to, right, de by dp, I'll write. In general, for any wave packet or wave group, okay, group velocity Vg equal to de by dp. So de by dp will give you what? Group velocity. Okay, right. So what is particle velocity? Phase velocity. Phase velocity v equal to omega by k. Phase velocity v equal to omega pi. Now for a free particle, what's a free particle? A free particle's total energy is entirely kinetic in nature. Free particle is one on which there are no external forces acting. When there are no external forces acting on any particle, the potential energy of the particle remains constant or will be zero. If it is a constant in terms, when I want to differentiate that, better to take it a constant, cannot be differentiated, isn't it? So I'll take the potential energy as zero only. So So free particle potential energy is 0. Kinetic energy, right, is the total energy entirely kinetic in nature. P equal to E equal to P square by 2m. Equal to P square by 2m. Now group velocity is d by dp. Right, now what is this velocity with which the particle is moving? V. Right, P equal to mv, where V is the velocity with which particle is moving. So if I differentiate this dE by dP in order to get the group velocity of a particle, dE by dP equal to, right, d by dP of P square by 2m, 2p by 2m, nothing but P by m. What is P by m? Nothing but particle velocity. Means for a particle, according to de Broglie, group velocity is always equal to particle velocity, we can write. Okay, now the problem, the difference between what you call this wave packet and particle problem has been solved with this. Okay, when you treat it as a particle, you will call it as particle velocity. When you treat it as a wave packet, you will call it as group velocity. But both are one and the same. Means if I throw this pen like this, classical physics says that particle is going up and coming down with some velocity v, right? Quantum physics says that wave group is going up and coming down with group velocity. Both are one and the same. Means the problem has been resolved like this. Okay, means the extended phenomenon of wave and the localized nature of the particle have been, right, what you call here, the people have a compromise here too. Now to what extent I can keep on localizing the particle like this as I keep on increasing what you call the number of wavelengths I consider, can I reduce this wave packet size? Okay, to what extent I can reduce this wave packet size? Means, is there any limit? That limit is set by the uncertainty principle. Okay, right? If you keep on increasing the number of wavelengths you consider, can you reduce the wave packet size to a single point? It is impossible. Okay, right? That is, there is one theorem in quantum mechanics called Renfresh Theorem. Okay, which says that, right, under the limits what you call the particle can be reduced to a point. Okay, quantum mechanics and classical mechanics will give the same result. Okay, we'll treat both are at large quantum numbers. Okay, quantum mechanics also gives same results as classical physics. Okay, right, means people in those days they were a little bit confused. The early physicists, wave phenomenon is totally different, classical physics is totally different. How to correlate these two? Niels Bohr has tried with his correspondence principle. Large quantum numbers, classical physics and quantum mechanics will be identical. Similar, Renfresh theorem says that if you keep on reducing the wave size of the wave packet to a single point, classical and quantum mechanics, right, will give the same result. That's the gist of what you call Renfresh theorem. Okay, but to what extent you can reduce the size of the wave packet? Not indefinitely. You cannot reduce the size of the wave packet to that single point. Okay, that is restricted by the uncertainty principle. Okay, right, you can reduce the size of the wave packet to the extent to which it obeys uncertainty principle. Extent to which it obeys uncertainty principle means I cannot exactly relate, okay, at the microscopic level, quantum and classical physics. Okay, right, so what is the limit to which I can reduce the size of the wave packet? Till the limit of what you call acceptance of uncertainty principle, in such a way as the delta x into delta px, right, cannot be less than h bar by 2, right? The minimum value should be h bar by 2. That is the extent to which I can compromise, or I can what you call correlate classical and quantum physics. Okay, this is the significance of uncertainty principle. Okay, now we will go into the group velocity aspect now. So in general, okay, wave or phase velocity is v equal to omega by k. Okay, group velocity in general is given as d omega by dk. Means if you divide omega with k, you will get its phase velocity here, not particle velocity. That aspect is gone. Right, if you differentiate omega with respect to k, you will get the group velocity of a group of waves. Okay, the problems will be coming like this. In a group of waves, the wave velocity or phase velocity is found to be proportional to, right, k square. What is the group velocity of that waves? Okay, right, means vp is proportional to k square. Means in order to get group velocity, you need this is nothing but d by dk of omega. Right, if you differentiate omega with respect to k, you will get group velocity. Means in order to find the group velocity, you must have this what you call omega value with you. You must have this omega value with you. He has given Vp is proportional to k square. What is Vp equal to? Right? Phase velocity is equal to omega by k is proportional to k square, or omega is proportional to k cube, or omega equal to c k cube. C is some constant I'll take. So now what is d by dk? D by dk of omega is nothing but c k cube. Okay, c k cube. D by dk of c k cube is 3c k square. 3c k square. Okay, what is c k square? C k square nothing but phase velocity. That is, group velocity is equal to 3 times the phase velocity. In this case, okay, in this problem, right, in a group of waves where phase velocity is proportional to k square, or phase velocity Vp equal to some constant into k square, ck square, group velocity is coming to be 3 times that of the phase velocity, because 3c k square it is. Okay, right, that is, here group velocity is more than the phase velocity. Okay, right, when group velocity is more than the phase velocity, okay, we call that is a dispersion. This is known as dispersion principle. Okay, if group velocity is more than the phase velocity, it is called anomalous dispersion. If velocity, it is called normal dispersion. If group velocity and phase velocity are equal, there is no dispersion. Medium is not a dispersive medium. Okay, non-dispersive medium. In a non-dispersive medium, phase and group velocities are in the ratio 1:1. They are always equal. In an anomalous dispersion medium, okay, group velocity is more than the phase velocity. In a normal dispersive medium, group velocity will be less than the phase velocity. Okay, right? So this is one simple example of what you call velocity when phase velocity is given. How to find out group velocity? Sometimes they'll give you omega directly. When omega is given directly, okay, your problem is simple now. Simply substitute the what you call the differentiate that omega with respect to k. Okay, you will get the group velocity whatever is asking. If he gives you phase velocity is omega by k. So multiply whatever phase velocity term he has given, multiply it with k, you will get omega, then differentiate it with respect to k. Okay, so many problems will be appearing in the exams, like in oceans. In seas and oceans, we have 2 types of waves. One is waves of large wavelength. Okay, they are called gravity waves. Okay, tsunamis are caused by those gravity waves only, where the wavelength of the wave will be 50 kilometers, 100 kilometers, 200 kilometers, like that. The wavelength will be so big. Okay, right? And also there are surface tension waves. Okay, the surface tension waves. Okay, it is nothing but 2 pi t by some rho lambda under rho. Okay, this is the phase velocity of surface tension waves whose wavelength is small. Okay, whose wavelength is small. The surface tension waves are ripples, we call. Okay, the waves which we see on the shore of sea, in beaches, what we see small waves coming, and what you call, the waves will be coming like that. Suddenly the amplitude becomes maximum and keeps on hitting. That is a fun for those who are enjoying on a beach. Okay, right? They are nothing but dispersion waves or surface tension waves, or low wave, less velocity, less wavelength waves. Okay, their phase velocity is given as 2 pi t by rho lambda, where rho is density of the medium, that is water. Okay, t is surface tension in the medium. That's why they are known as surface tension waves also. Okay, there are another type of waves, tremendously large amplitudes of hundreds of kilometers. They are called gravity waves. Okay, right? Gravity waves, V equal to their phase velocity is given as root g lambda by 2 pi. Root g lambda by 2 pi. Okay, right? Here lambda is very large. Here lambda is very large. For small values of lambda, this gravity waves will not be of any significance. Okay, similarly for large values of wavelength, here surface tension waves are insignificant. So surface tension waves are significant for waves with small wavelength. Gravity waves, okay, that phenomenon is applicable for waves having very large wavelengths. Okay, these are called gravity waves, these are called surface tension waves. Okay, now look at the velocity wavelength relation. Okay, look at the velocity wavelength relation. Here velocity is inversely proportional to lambda. Here velocity is directly proportional to lambda. Of course, under square root. Okay, V is proportional to 1 by root lambda. V is proportional to root lambda. Depending on that itself, we can tell whether the group velocity will be more than phase velocity or less than phase velocity. Well, means whether those waves suffer anomalous dispersion in that medium or normal dispersion in the medium. Okay, how do I do that? Okay, right, phase velocity is equal to omega by k, or omega equal to kv. omega equal to kv. So what this is? Phase velocity v. Okay, now group velocity vg equal to d by dk of omega. Okay, omega equal to kv, that is d by dk of, right, k into v. Okay, so if I differentiate this, d by dk, product rule. Okay, right, so group velocity vg equal to k into dv by dk plus v into dk by dk is 1. So group velocity is equal to v plus k into dv by dk. This is one relation between the phase velocity and group velocity. What is this term dv by dk? Right, rate of change of velocity with k. K value means k equal to 2 pi by lambda. Okay, means as for different wavelengths, if they have different velocities, that is known as dispersion. What is the meaning of dispersion? In a medium, if different waves travel with different velocities, the medium is said to be dispersive. In a medium, if all waves are traveling with same velocity, okay, the medium is non-dispersive, we say. This dv by dk is a measure of dispersive power of the medium. Dispersive power of the medium. Now, v equal to, what is that wavelength? V equal to, let us take it in terms of wavelength. K equal to 2 pi by lambda. Okay, so dk will be equal to, okay, right, what is that? d of 1 by lambda. Okay, that is nothing but minus 2 pi by lambda square into d lambda. Okay, if dk, k equal to 2 pi by lambda, dk equal to minus 2 pi by lambda square into d lambda. Now substitute those values and simplify. Wherever k is there, put 2 pi by lambda. So vg equal to, okay, so vg equal to, k is nothing but 2 pi by lambda into dv by dk. That is dv by, what is dk equal to? Minus 2 pi by lambda square into d lambda. Okay, again v only, like this, again v. Now slight rearrangement of terms here. Okay, right, this 2 pi and this 2 pi gets cancelled. Okay, one lambda also gets cancelled, so this lambda goes up, so this is equal to v plus lambda into, now this minus sign is there. Okay, so it is minus v minus, right, this lambda also goes up, v minus lambda into dv by d lambda. This is another expression for group velocity, right, in terms of wavelength. This is expression in terms of v plus k into dv by dk is in terms of k. Okay, vg equal to v minus lambda into dv by d lambda is second expression, right, the relation between phase velocity and group velocity in terms of wavelength. Okay, now look, this dv by d lambda. Okay, dv by d lambda is known as, is a measure of dispersive power of the medium. Okay, if all waves travel with same velocity, means velocity is not changing with wavelength, dv by d lambda equal to 0, we will get vg equal to v, right, the medium is non-dispersive medium. Okay, the medium is non-dispersive medium. Okay, now if dv by d lambda is positive, if dv by d lambda is positive, vg equal to v minus something. Okay, vg equal to, okay, if, now case 1, if dv by d lambda is equal to 0, right, vg equal to v, the medium is non-dispersive, means phase and group velocities are equal. Okay, second case, if dv by d lambda is positive, dv by d lambda is positive means what? When do we get dv by d lambda positive? When lambda is increasing, if velocity is also increasing, means if greater wavelengths are traveling with higher velocities, lesser wavelengths are traveling with lesser velocities, means in a medium, right, a wave having more wavelength is traveling with more velocity, a wave having less wavelength is traveling with less velocity. Okay, then we say dv by d lambda is positive. If dv by d lambda is positive, what will happen? Vg will be v minus something, v minus something. Okay, so vg will be less than v, vg will be less than v. Okay, in a medium, if the group velocity is less than the phase velocity, the medium is said to be, right, normal dispersive medium, or this is called normal dispersion. Okay, normal dispersion. Okay, now the third case is, if dv by d lambda is negative. What is the meaning of dv by d lambda becoming negative? Okay, if dv by d lambda is negative means what? When will we get that dv by d lambda negative? Right? If lambda is increasing, suppose a velocity is decreasing, or lambda is decreasing, velocity is increasing. Both are moved, what you call moving with opposite sign. If lambda is increasing, right, velocity decreases, or lambda decreases, velocity is increasing, say, then we say that dv by d lambda is negative. Okay, means in that medium, longer wavelengths travel with lesser velocity. Okay, smaller wavelengths travel with more velocity. We can change this in terms of frequency also. In terms of nu I can write, in terms of omega I can write. Okay, you take it as what you call an exercise. Okay, in JNU exams, HCU exams, right, they'll ask sometimes in terms of frequencies. Write this expression. What is that? Vg equal to, right, v minus lambda into dv by d lambda. Write that expression in terms of frequency. Means instead of lambda into dv by d lambda, I want some frequency term. Okay, dv by d nu I want. Okay, sometimes they'll ask it in terms of angular frequency. Okay, what is the relation between group and phase velocities? Okay, right. So I'm not doing that because we see velocity v equal to nu lambda, mu equal to v by lambda. So d nu equal to whatever you get, you see, substitute that, have that formula in your hand. Similarly, right, we have got in terms of k, dv by dk, right, omega by k equal to v. Okay, in terms of omega also you try to keep those formulas in your hand ready made. Then and there in the exam, if the question comes in terms of omega, you can do it, but you will be wasting 2 or 3 minutes of time. But you practice it now itself. Okay, that you do it as a minimum exercise for yourself. Okay, to get involved in this topic, right? So Vg equal to, what is d? Okay, now what is dv by d lambda negative means what? If longer wavelengths travel with lesser velocity, or lesser wavelengths travel with smaller wavelengths travel with a higher velocity, we say that dv by d lambda is negative. When dv by d lambda is negative, what will happen? Okay, when dv by d lambda is negative, okay, dv by d lambda is negative, what will happen? Vg equal to v plus something. That is, Vg will become greater than v. Vg will become greater than v here. Okay, here Vg will be greater than v, that is called anomalous dispersion. Anomalous dispersion. Anomalous means what? Abnormal. Okay, normal, anomalous. Anomalous means abnormal dispersion. Abnormal dispersion. Higher wavelengths are traveling with lesser velocities. Means higher frequencies travel with higher velocities. Lesser frequencies travel with lesser velocities. That gives rise to anomalous dispersion. Okay, so whether the medium is dispersive or not, it depends on dv by d lambda. If all wavelengths travel with the velocity, same velocity, right, the medium is non-dispersive. Now just example, what type of waves? Just now you can apply physics to our everyday life. Which waves are non-dispersive, which waves are dispersive? Okay, what waves do we see? Most prominent waves are sound waves and light waves, that's all. Okay, now look at sound. Okay, right, see, my voice is of one frequency, another person's voice is of another frequency. If 101 people are talking in a room, okay, person standing say 100 meters away from this group of people, if you listen to all these sound waves simultaneously, okay, means, right, different people are having different frequencies, right? So if all frequencies or all wavelengths are traveling with same velocity only, right, they will reach the ears of the observer simultaneously. Means what? Right, all sound waves are traveling with same velocity of sound, that is 330 or 332 meters per second. So sound waves are non-dispersive in air. In air, right, sound waves are non-dispersive. Okay, best example is orchestra. Okay, in your college annual day celebration, the people invite one orchestra team where a boy will be singing, girl will be singing, one fellow will be what you call playing flute, other fellow will be playing drums, etc. Guitar frequency is different, flute frequency is different, drums frequency is different, boys voice frequency is different, girls voice frequency is different. But the students all enjoying, right, in front of that dash. Okay, suppose the dash is 100 meters long, the stadium is 100 meters long, the fellow is sitting at the end, right? He will listen the entire, that if you listen all things are simultaneously, it is known as music, isn't it, right? He will be able to listen the sound of coming from flute, sound coming from the boy's voice, sound coming from the girl's voice. For all 101 instruments there, having different frequencies, they will reach his ear simultaneously. That is known as music. It will never happen that first what called boy's voice will be heard, after that guitar will come to your to your ears, after that slowly flute music will come to your ears, after that some girl's voice will come. No. Okay, right? All voices of all different wavelengths will reach your ear simultaneously. Means all sound waves are traveling, all wavelengths are traveling with same velocity, isn't it? So sound waves are non-dispersive. Similarly, light also. Okay, white light contains 7 colors, Vi, Bg, Yr, from 3500 angstroms to roughly 7000 angstroms. Thousands of angstroms are there. All thousands of angstroms of electromagnetic waves, right, in that region from 3500 to 7000 is known as visible light. They are reaching your eyes simultaneously. That's why white color is seen everywhere. Okay, so white light is non-dispersive in air, we call. Okay, but same light when I send it, white light when I send it through prism, right, that is getting split up into 7 colors, Vi, Bg, Yr, like this. So when you pass light through a prism, what is happening? Okay, Vi, Bg, Yr, right, 7 colors will be split up. We call this as dispersion. Why white light is getting split up into 7 colors? Because 7 colors have different wavelengths. Different wavelengths are traveling with the different velocities. Okay, that's why they cannot go together now. So they get separated. Okay, and the medium is what you call the prism medium is dispersing them. Is dispersing means it is making different wavelengths to travel with different velocities. Okay. Now from here also we can tell white light is bending more means refractive index for violet light is more. Okay, red light is bending less means refractive index is less for. A refractive index means ability for the medium to refract the incident light. Okay, right, refractive index for red light is less, refractive index for violet is more. Okay, now what is happening? White is bending more because it's refractive. V equal to C by N, we write. If refractive index is more, velocity will be less. Refractive index is more means what? Violet light will be bent more. Okay, because its velocity is it is bending more means it is experiencing more refractive index means violet light velocity will be less. When violet light velocity is less, as wavelength is less, violet wavelength is less, red wavelength is more. Okay, wavelength is 4000 angstroms to 7000 angstroms. Because this violet light is bending more, I say refractive index is more for violet light. When N is more, velocity will be less here. Means velocity for violet light is less, right? Velocity for red light is more. Okay, red wavelength is more means as wavelength is increasing, velocity is also increasing. Okay, carefully observe here. When the wavelength is increasing from 4000 to 7000, velocity is also increasing. That is dv by d lambda. As lambda increases, velocity is also increasing. How do I know that velocity is increasing? Red light is bending less than violet light. Red light is bending less than violet light means refractive index for red is less, velocity is more. Okay, so dv by d lambda will be positive. Okay, when dv by d lambda is positive, right, Vg will be less than V. It is known as normal dispersion. So visible light experiences normal dispersion in the medium of prism. In light, visible light is non-dispersive means air is non-dispersive for light waves. Air is non-dispersive for sound waves. Okay, right, but in prism that depends on the property of the medium. Okay, so light experiences normal dispersion in a prism. Okay, similarly means by looking at dv by d lambda, you can tell, right, whether those waves suffer normal dispersion or anomalous dispersion. Now let us go back to that example of gravity waves. Okay, gravity waves, what we have seen, I told you there are 2 types of waves in ocean, okay, or in seas. Okay, one is longer wavelength components called gravity waves. Okay, these are known as gravity waves. These are called surface tension waves. Okay, of course we can calculate what is the ratio of my beams. You have to differentiate dv by d lambda, substitute in that, but by just looking at the expression itself we can tell. as lambda is increasing, in terms of gravity waves, velocity is increasing. Means what? d by d lambda is positive means, right? For those waves, right, group velocity d by d lambda is positive means what? It is normal dispersion. Velocity will be less than, group velocity will be less than phase velocity. Means gravity waves suffer normal dispersion. Okay, what about here? As lambda is decreasing, velocity is increasing. Means for these waves, d by d lambda is negative. That is, Vg will be greater than V. Means these waves suffer anomalous dispersion. Okay, these waves suffer anomalous dispersion. So now 2 pi T by rho lambda tension and the density of water will remain constant in ocean. So you can write this as V equal to, right, under root C by lambda, or root C can be taken as some constant. V is proportional to, or V equal to, only you take some constant K, not K. So you take something like A. Okay, K is used for something else, isn't it? So A, right, lambda to the power minus half. Okay, V equal to A lambda to the power minus half. Find out dV by d lambda. Okay, you can find out the ratio of group and phase velocities. That's how problems will come. When what you call phase velocity is given by 2 pi T by rho lambda, what is the relation between group and phase velocities? That is another problem. Okay, right. So this is about the what you call wave and group velocities extensively, right? They are applicable in waves and oscillations and waves, as well as in what you call unsteady principle also, because we have to relate what you call the wave aspect of particle and the particle aspect. Okay, so this is about the significance of wave and group velocities. We will solve some problems in the next session. Okay, thank you.